All right, this is page 340, number 4, and we're going to treat this two different ways to show you how to solve the same problem two different ways. So we have an external force causes a box to move up a constant speed up the ramp. The friction force between the ramp and the box is negligible, and the external force is exerted on the box in a direction parallel to the ramp. So the first part asks for a free body diagram. So gravity is acting on the box. The applied force is in the same direction as the ramp, and there's our normal force. So for part B, we're going to treat the box as an object. Okay, now remember, an object can only have kinetic energy. It cannot have gravitational potential energy or spring potential energy. There's no spring here. The external force here, part B, we're going to treat the box as an object upon which the external force is exerted over a distance of 5 meters, while the velocity remains constant. And we're going to apply the work-energy theorem to evaluate the numerical value of the work done by this force. So we've got our, let me draw this here. We've got our distance here, which is 5 meters. Okay, it's going to go up the ramp 5 meters. Let's see. The mass of the block is 3.5 kilograms. This height here is 3 meters, right? This length here is 5 meters, okay? Which should tell you you can solve the rest of the triangle, but we'll solve that in a moment. Now the applied force, okay? The applied force is actually equal to mg sine theta, and here's how I know that. It's a constant speed, so the forces are balanced in the x direction, and with all inclined planes, almost all, we have our axes like this. So if I draw my sort of faux free body diagram here and I break my gravitational force into components, right? My mgy is mg cosine theta here, and that's balances the normal force. My mgx is equal to mg sine theta, okay? So along my x-axis, which is along the ramp, the speed is constant, so there's no acceleration, which means the forces are balanced. So I can write Fa equals mg sine theta. So now I have an actual value for this force. So what is the work done by the applied force? It's the force times the distance times the cosine of the angle in between the applied force and the displacement. But the applied force and the displacement are going in the same direction, so that's a 0. So the work is the applied force times d. Now, we know that the applied force is mg sine theta times d. I know all of those answers, okay? Now, they did not give you the angle, but this is a 3, 4, 5 triangle, right? So you can calculate this angle, but I didn't even do that because I know the opposite side and the hypotenuse, so the sine of this angle is literally 3/5. Okay, I don't think I've ever had a problem like this before, but we don't need the angle. You can calculate it if you want, but I guarantee you'll get 0.6 for the sine. So what I get is 103 joules of work done by the applied force. Okay, because I treated the box as an object. Okay, the applied force is going to do some work on it. Now, they didn't ask this question, but I will say that gravity is also doing work, right? In an amount of, guess what? mg sine theta in the negative direction. So the net work done on this box is actually 0. The applied force does 103 joules, gravity does 103 joules, no net work. This should be okay because we didn't add any energy to the system because the box is still moving at a constant speed. So that wraps that up all in a package there for you. Now, part C says, okay, well now treat it as the box and the earth as a system upon which the external force is applied. Okay, so if the system is the box and the earth now for part C, box plus earth. Okay, we still have that applied force, okay, but work is going to affect a change in mechanical energy, which is a change in kinetic plus a change in gravitational. Now, the box is still not changing its speed, so its kinetic energy is not changing, okay? So we have the work is equal to the change in gravitational potential energy. And that makes sense because what happened to the box? It started here. Gravitational potential energy is equal to 0, if you want to call this H equals 0. Final gravitational potential energy is mgh. All right, and remember this height is 3 meters. So we have 103 joules. So in this situation, the external work on the box Earth system results in a change in gravitational potential energy, and that change is 103 joules. And it's very important that the answer is the same no matter how you do it. So this was an example of a problem that we did with the box as the system and then the Earth and the box as a system together. So I hope that helps. Let me know if you want to discuss it further.